Hello my dears, how are you all? So in the last class we discussed about some importance problem regarding the maximum torque, right? Efficiency. It is a practice set 2, right? It was a practice set 2. So carefully do that problems, because in questions anything may ask, right? Anything may ask in your examination. So be prepared. That is the main thing. So today we are going to take some important portions. That is actually, we need just the equations. Okay, we just need the equation. We don't want the derivation and all. So first of all, let's see the relationship between full load torque and maximum torque. Full load torque and maximum torque. There is actually in your university examination and all, right? There was a big derivation, no? So by deriving those, we will get a final result, right? We will get a final result. But we just need that final result only. But because we are taking our class in point of our examination, right? Our examination, that is in objective type, right? That is in objective type. So we don't that big derivation. We don't want that big derivation and all. We just need the equation. So you just remember this equation: TFL by T max is equal to 2 into S into ST max all divided by S square plus ST max the whole square. Just you need to know this equation. This S is nothing but full load slip, and ST max is nothing but slip at maximum torque, correct? Maximum torque. What was the condition for slip at maximum torque? It will be R2 dash by X2 dash. Am I correct, my dears? R2 dash divided by S2 dash is the ST max. And that's all. That is the equation. You just need to remember this equation. Okay. You don't want to go for the big proof and all, because it's time consuming. It's not at all needed. If you prepare for SSC mains, SSC JE mains, then there will be theory questions. But we focus on SSC primary side now. SSC tier 1, right? We are focusing in that first. Then we will go to theory session. Okay. So this is the equation for TFL divided by T max. You just need to remember this equation only. And let's discuss another. It is nothing but relationship between starting torque and maximum torque and the maximum torque bodies. Here also we just need T start by T max is equal to 2 into ST max. It is nothing but 2 into 2 divided by ST max plus 1 divided by ST max. Okay, it is rarely, no, it is just for our safety. We just want to know this for our safety only. In examination, these type of questions, no, it's almost hard to see this type of question. But anyway, we have to learn this. You don't want to write the equation in your examination, but you may ask suppose you may directly give the directly give the answer like this, or from the option you want to take the answer. Then these things will be very useful, correct? But terminology may change. Suppose ST max, simply they represent ST, or simply S may represent like SFL. That terminology may change, but the fact is same. Okay? So TFL divided by T max will be equal to these two equations. Now my dears, you have to remember. Okay, just that's all. And next, Next we have to see speed regulation. We already learned that speed regulation in induction motors. The equations for the speed regulation is nothing, my dears. It is nothing but N0 minus NFL divided by NFL into 100. That is the percentage speed regulation equation. So percentage speed regulation is nothing but no load speed minus full load speed divided by what is that? NFL. So it is, in other words, is it simply N into ns minus NR divided by NFL divided by NFL. Correct. That is the correct. Because no load speed is nothing but the synchronous speed. No, it's wrong. Because ns is nothing but the slip speed. We almost take in that manner, but we can't exactly write this equation. It is actually equivalent only, not exactly, because N0 is nothing but the no load speed of the rotor, not the synchronous speed, right? So better you just write this only. It is equal to no load speed. I will write. It is different, right? That is why. No load speed and NFL is nothing but full load speed. NFL is nothing but, my dears, full load speed. Okay. So in your problem, suppose if you want to do, you just give the synchronous speed and you just give the rotor speed. Then you have to, suppose you want to calculate the speed regulation. Then ns minus n, you did it in one problem, right? Ns minus n divided by n into 100. That is the speed regulation. That also speed regulation in terms, suppose if the no load speed and full load speed separately not given. No load speed is that much and full load speed is that much. It is not given directly. Then you can go for this no load speed is nearly equal to the synchronous speed, and what? This n will be nearly equal to the what? NFL will be nearly equal to the NR or simply N. Is it clear? I remember that problem. I know in that problem we did what? NS minus N divided by N, right? That is the regulation. That also regulation. But the exact equation is this. Exact equation is this if you directly given the no load speed as well as the full load speed. Unless it is mentioned no load speed and full load speed, you can take no load speed is equivalent to NS and full load speed is equivalent to NR. But that will be the regulation. Okay, don't confuse. That is a fact. So that's all about the regulation. And nearly 3% to 5% will be the regulation of induction machine. Induction motor. That means it's an excellent or regulated machine, right? 3 to 5% means it's not that much, variation. As much as the regulation value is lesser, voltage regulation or speed regulation value, any regulation value is lesser in terms of percentage, then that is a very good system. That is a very good. For example, suppose you have a system having 10% regulation, voltage regulation or speed regulation, anything. 10% regulation, another system having 2% regulation, another system having 2% regulation. Which is the best system means this will be the best system. Because in the system, 2% means not that much variation from no load to full load occurs in the motor or any bus or something like bus in the sense load bus, right? Transmission system. Okay, so that is the meaning of the regulation and the importance of regulation. Is it clear? And positive regulation will be regularly I will explain in power system. Okay, that I will explain in power system. So that is the concept of what speed regulation. These are small topics, my dears. That is why. So you just remember this what number 3 to 5% will be the normal range of regulation of what? Induction motor. Okay. Next you have to see the This is somewhat important. Starting of three-phase induction motor. Starting of three-phase induction motor. So why there is a need of starters, my dears? Starters are simply what? Starters are, in order to, the name itself indicating the function of a starter. What is that? In order to start the machine. But in order to start the machine, because something there should be in order to start a machine, no? In order to start a machine, no? Depending upon the requirement, there should be something to start a machine. That is called the starter. So the starting of three-phase induction, there are three types of starting methods. One is direct online starting. Online starting. Or sometimes it's called DOL starter. And second is star delta starting. Star delta starting. Star to delta starting. And third one is auto transformer starting. Starting. Okay, so let's discuss these, what direct online and star delta and auto transformer one by one. First of all, direct online starting. Direct online starting. Listen, direct online starting means, see, I will explain a very interesting fact and a very confusing fact too. This is nothing but the starter, and this is nothing but our stator. This is the rotor and this is the stator. This is nothing but our supply. This is nothing but our supply. The function of the starter is to, there are two main functions of starter. Okay, functions of starter. Functions of starter. One is to reduce high starting current. To reduce high starting current and to avoid overload or under voltage. What, my dears? To avoid overload or under voltage. So these two are the important functions of a starter. Why we are using starters in induction motor? This is the reason. We have to reduce the high starting current, because at the instant itself you switch on the motor, initially a very high starting current may flow, because the stator, the induction motor stator is similar to the short circuited condition, because stator winding is short circuited. There is no load in the stator actually. The stator winding itself is like a simple conductor. Wow. That means it is simply like, you have, suppose for the simplicity, you just take phase and neutral. Stator means it simply after some winding it will come back. That means there is no load, there is no heavy resistor there. So initially there is a possibility of absorbing very high starting current, my dears, very high starting current. So in order to reduce that starting current, we need starter. Otherwise, if you directly switch on the supply means, if you directly online starter is also there, but it is not that much safe. It's not that much safe compared to the other two. Because if you directly switch on the supply means a direct high inrush current will be flowing. That current value will be let for this direct online starting. Let ISC equal to IST, or simply like this. Let I start is equal to ISC happens there. If you directly online, I'm talking about this direct online starting. Okay, the function of starter is over. I'm talking about the direct online starter now. So direct online starter means you can directly switch on the supply. You just connect a motor, you can directly switch on the supply. So the function of the starter here is that in order to reduce the starting current. See, in stator of the induction motor, it may be either star connected or delta connected. Okay, that's depending upon our demand or our need. We don't bother about that stator winding connection and all here because we are dealing with the starters now. So our area of concern is just this. Not the stator winding is in star or this is in delta. We don't want to know that. We want just our starter is how it work. Our starter how it work. Just that only we need. Okay, because in preceding session now you will feel, in continuing session, that means the next starter no star delta starter, there you feel a very big confusion. That is why initially I am saying our area of concern is just for our starters. Not we want to know our stator winding is star or delta connected, my dears. Okay, so I already saying this one. So first of all, direct online starting. So you know the functions of starter, bit to reduce the high starting current. Next, to avoid overload or under voltage. Overload means again high load. If you apply a very high load means then also the current will be very high. In the rotor side, if you apply a very high load means, that means a very high load in the rotor side means what is the meaning? You resist the motion of the rotor. That is the meaning of the load in the rotor side. You resist the motion of the rotor. That is the meaning of load. No? Suppose the motor is smoothly, rotating. If someone is trying to block that motor, then we can say that there is some load applied. There is some load applied. So load in the motor is nothing but what? The difficulty to run the rotor side. The difficulty in running the rotor side is called the load in terms of what? Motor. Okay, so to avoid the overload, suppose the load is heavier, then also there will be high inrush current, there will be high current which is flowing from the stator side because it has to compensate. The rotor must turn. The rotor must turn so that it has to absorb more current from the stator side. It is similar to the short circuiting of the transformer. Short circuit of the transformer. If you short circuit the terminals of the transformer, then high current will be flowing. You know the short circuit test. Did you remember that? The short circuit test. The high current will be flowing in the primary side. Similarly, there will be high current flowing in the primary winding of the what? The induction motor also. That means the stator winding also. So to avoid the overload or under voltage. Under voltage means suppose the voltage is very low. We can't start the induction motor. It will not pick up to the speed. It may heaten. It may tend to heaten up the winding. So we have to take care of that under voltage condition also. That under voltage condition also we have to take care. So in order to take care of the overload, under voltage, over current, high starting current, for all we need a starter. Okay, so we are focusing on this part only, not on this part. Yes, this part only. Okay, so first of all, direct online starting. Why I came here and came there, came here and came there means it may make confusion. It may make confusion. That's right. Okay, so we have to see direct online starting. So direct online starting means, my dears, you just switch on our three-phase induction motor into the supply and just on. Just on. What happens then? The starting current will be flowing at that time will be simply the short circuit current, where IS is nothing but, my dear, short circuit current. Short circuit current. Short circuit current. Because you directly switch on the supply means this thing will happen there. This thing, because there is nothing in the stator. As a load there is nothing in the stator. You simply switch on the supply. We are not bothered about this rotor now. We are not focusing on that area because our area is simply stator side. Okay, so what happened? You switch on the supply means there is a high starting current flowing. Let that starting current be ISC. The ISC will be utilized. Okay, I will tell later. So this is the starting current. Then Okay, so this will be the starting current. So we have the starting torque equation in terms of the rotor current and rotor resistance is that, starting torque will be equal to 1 by omega s into I2 dash square into R2 dash. And full load torque equation in terms of, again, the omega s and the rotor current is that I2 dash square into R2 dash by s. So these are the two equations of starting current and full load, two equations, starting torque and full load torque in terms of omega s and I2 dash and R2. There are so many equations connecting T start and TFL in different parameter, but this is very, very important in terms of currents. In previous when I started my lecture, we starting torque, full load torque, starting torque, maximum torque, there was a relation, no? That is a final relation. That is a final relationship between starting to maximum and full load to maximum. Okay, but this is the equation for starting torque and this is equation for full load torque. So starting torque in terms of I2 dash and R2 dash, full load torque in terms of I2 dash and R2 dash. This is the equation. Then what will be the starting torque by full load torque? It will be equal to, let be equation number 1, my dear, that will be equation number 2. Then 1 by 2 will be give what? 1 by omega s into I2 dash square into R2 dash whole divided by what is that? Whole divided by 1 by omega s into, what is, my dears? I2 dash square into R2 dash by s, correct? This full load let be ISFL. So it will be SFL. Correct? So this and this will cancel. This R2 dash will cancel. Okay, this I2FL. Okay, this is I2 dash in terms of I2FL. Okay, 1 by FL, 1 by I2 dash. Let be, this is be I2 dash at starting and this will be I2 dash at FL. So simply you can write like I2 start divided by, or simply I start. You can write like I start. Okay, you can write like I start by IFL the whole square into SFL. This is very, very, very important relation. Only you just need to remember this equation. The starting torque by full load torque will be equal to I start by IFL the whole square into SFL. Where I start is nothing but, my dears, I start is nothing but what? The starting current. I start is nothing but the starting current, and this I2 dash, you are confusing with this I2 dash now. But what was that I2 dash? In the equivalent circuit, do you remember that? In the equivalent circuit, no? In the equivalent circuit, there is I2 dash. There is I2 dash, my dears, in the equivalent circuit. See, R1J X1, R2 dash by S and J into X2, R and J into Xm. Did you remember that equation? This current is I2 dash. This current is I2 dash, which is nothing but the primary current. Itself. That means the stator side current is the same that I2 dash. Okay, don't confuse. Please, I am saying, please watch this video if you clearly know the previous lectures. Otherwise, it will be a very difficult task to understand. Okay, so this will be the I2 dash. Okay, so this I2 dash I can replace this I2 dash at starting as IST. This I2 dash at full load be IFL. It's my wish, no? So I can do that. It's my wish, right? So this is the equation for T start by TFL, that is equal to IST divided by IFL the whole square into SFL. Okay, so for direct online starting, this IST will be equal to what, my dear? ISC. So for direct online starting, for DOL starting or direct online starter, T start divided by TFL will be equal to, what is that? I start is nothing but ISC divided by full load current is again full load current, there is no change in that, into SFL. So this ISC is nothing but short circuit current when we directly switch on the supply. That is the ISC. Okay, please remember this. So that is the equation for starting torque to full load torque in terms of what? DOL starter. This equation you want to know. This equation is very important. This you have to remember. This you have to remember. Okay, so let's move to star delta starter. Okay, let's move to star delta starter. Star delta starter. Second one is star delta starter. Okay, so first we have to learn what is actually in star and delta connection, what is happening. This is star, my dears, this is star, and here I will draw this. This is delta U of this. Okay, so this is the star current, let be I star. This is the voltage, that is be V1, and this is the Z impedance per phase. And what will be this IY, my dears? That will be this IY. This is nothing but the star connected line current, correct? Star connected line current. This star connected line current will be equal to the voltage across this by the impedance. Am I correct? And this voltage will be what? It will be V1 by root 3. Am I correct? Because this is the line voltage. So phase voltage will be root 3. Line voltage will be root 3 times phase voltage. So phase voltage will be line voltage by root 3. Am I correct? So star current will be equal to, what is that? V1 by root 3 into Z. This is the star current. In terms of delta, suppose this is the same V1, that is nothing but the line voltage, and this is nothing but the delta line current, and which is nothing but in terms of phase current. Suppose this is the phase current, delta phase current, then this phase current will be what, my dears? This phase current, suppose this is Z, this is Z, and this is Z. Okay, this phase current will be what? This phase current will be, let be I phase. I phase will be what? I phase will be equal to V1 divided by Z phase. Correct? This is Z phase. These are the Z phases. So simply Z. You can take simply Z. So V1 by Z. But we need the delta, no? We need the delta, no? So in a delta connection, what is the relationship between the line and the phase quantity? I delta is nothing but the line current. Correct? Line current, which is nothing but what is that? Root 3 into V1 by Z. That is the phase current bus. So this is the I delta. This is the I delta. So this is the I star and this is the I delta. So what is I star by I delta, my dears? I delta. What is that? V1 by root 3 into Z whole divided by root 3 into V1 by Z. V1 by Z would cancel, right? So it will be simply 1 by 3. Correct? So I star will be, I star by I delta will be equal to what? 1 by root 3. Or I can say that I star will be equal to I delta by root 3. Sorry, by 3. So what you infer from this? What you conclude from this, my dears? What you conclude from this? If you are using, we are dealing with star delta starter. So how it work? So when you switch on the supply, the starter winding, not the stator winding, my dears, not the stator winding, the starter itself, it have a certain winding, and that winding, we connect that winding in star. So what happens? That star connection, suppose the motor is slowly pick up, right? When we start, the starting current will be reduced. I delta by 3. So reduced current will be applied there. So what happened then? When the machine start running and when slowly it pick up speed, normal speed or running speed, okay, what happened? Or nearly 80% of the what it rated speed, what happened? We shift the connection to delta. Okay, we shift the connection to delta. So what happened means it will be delta connected. It will be in delta connected. So what is the advantage of doing that? So initially it was in star. So we reduce the starting current by 3. We reduce the starting current by 3. It is now in delta. Okay, no problem. Because starting is the high current position. High current region is the starting region. So now it is in delta. Okay, no issue. So initially it may be it is in star connection, and after some time when the rotor picks up the normal speed, it will convert it to, that means the rotor winding itself arranged into what? We are manually arranging. Okay, first there is a switch, actually there is a switch or connection pattern. We can connect it into star, and again we can connect it into delta. That is the meaning of star delta starting. Okay, so initial starting current will be reduced by 1/3. Okay, I delta is nothing but when the machine is in normal running condition, that is the I delta. That current is I delta current. And that I delta by 3, that much current will be reduced. That much current will be reduced in the star delta starting. Okay, then we have to derive the equation for T start by TFL. T start by TFL. So T start by TFL in what, my dears? In star delta starting. Okay, in star delta starting will be equal to, what is that equation? Again we have IST divided by FL the whole square into SFL. Am I right? IST by IFL the whole square into SFL. So we have to apply that in terms of ISC. It will be equal to 1/3 into ISC divided by IFL the whole square into FS. This equation you have to remember. How this equation came? Okay, let's check that also. Okay, you may have a confusion, I know. I will check that also. So at the starting, IST divided by IFL, we have to see that first. So IST is nothing but, my dear, starting current. So I already represent IST equal to what? ISC, correct? That is the short circuit current. So that means what? IST means what? Short circuit current. Okay, we initially assumed that IST is equal to ISC. So in terms of ISC, we want to derive the equation for both three starters. We have to derive the equation for 3 starters in terms of ISC. Remember that. Not the starting current of that particular starter. Full load is actually, anyway, the full load means the rotor is in normal running condition. The starting is the problematic phase or problematic range. So that region is the area of concern. So I start, we already assumed I start is equal to what? ISC. So it will be equal to ISC divided by IFL. IFL is nothing but the full load current. So at full load current, the machine is in delta. Suppose the machine is in delta, then we can say that delta line current will be equal to √3 times the delta phase current IFL. Let IFL be the normal phase current. Okay, IFL be the normal phase current of the what? Machine in normal running condition without using any star transformation and all. When direct online starting, no. If you direct online starting, let IFL be the normal running condition or full load current. That is it is IFL. My dears, we are comparing with the DOL starter every time. This I start is nothing but the starting current of the DOL starter. This IFL is nothing but the starting current of the full load current of the DOL starter. We are going to convert it into star delta to starter. Then what happens? The ISTs, there is no change, but in IFL is nothing but the full load current. Now the full load current in what? Star delta starter. So now this is in delta. Now this is in delta. That means IFL is in delta. Full load current is now in delta. So delta is nothing but, in delta connection, √3 times of IFL will happen, right? In delta connection, this IFL is what? This IFL is what? This IFL is nothing but, without using any starter, you directly switch on the supply. That phase current is nothing. That is the IFL. That phase current is IFL. Suppose you convert it into delta, then it will be root 3 into IFL. So root 3 into IFL, the whole square into SFL. Okay, which will be equal to 1 by 3 into ISC divided by IFL into SFL. Okay, so that is the what? T start by TFL of DUL starter. Okay, this equation you have to remember. If it is confusing, then please read it again and again, you will get the answer. If not possible, in order to imagine, then you simply by heart this equation. Okay, this derivation side and all, no one will ask you, but you just need to want to know this. Okay, so that is the equation for starting current to full load, starting torque to full load torque in terms of DUL starter, right? Starting torque to full load torque in terms of DUL starter, my dears. Okay, so that's ISC by IFL, correct. Next you have to see the next starter is nothing but our auto transformer starter. This is very easy, no? The starter and the transfer, I think it's very confusing. Okay, it's very confusing, I know. So this is next you have to see auto transformer starter. Auto transformer starter is very easy. The function of the auto transformer is utilizing here. Okay. Okay, various. Listen, draw this. Draw this. Did you draw this? Did you draw? So auto transformer starter means the starter itself acts as an auto transformer, right? So we give a full voltage here. A reduced voltage will be available in the secondary side of the auto transformer. Am I correct? That reduced voltage, let ISC be the, ISC is nothing but V divided by Z. The applied voltage divided by total impedance will give you the ISC, that is the full load current, full current, or so simply the primary current when there is no tapping. Let ISC be the current, no? That ISC is same that of the direct online starting current, right? This ISC is nothing but the starting current of the DOL starter, okay? So this is the ISC. Then when tapping, to this portion, tapped portion is portion X. This current will be, I1 will be equal to X time ISC. How it's arranged? How we obtain this X time ISC? I will say. So the tapped portion voltage will be nothing but, my dears, it will be equal to, suppose the full voltage is V, then the tapped voltage will be, of course, less than V voltage will be there. So the voltage available across this will be equal to X time as that of V, correct? Or X time as that of the V, correct? So I can write like the tapped voltage will be equal to X time as that of the applied voltage, correct? X time as that of applied voltage, or tapped current will be equal to X times the applied voltage, correct, divided by Z, correct? X times the applied voltage divided by Z. Am I correct? So it will be X times into ISC. So this X time ISC is the current which is directly you fed to the stator winding of the motor. So that what happened, the starting torque divided by the full load torque in terms of auto transformer, in terms of auto transformer starter will be equal to what, my dears? What is that? Again IST divided by IFL the whole square into SFL, which is nothing but ISC divided by IFL is nothing but the starting current is reduced by X time ISC, no? So X time ISC divided by IFL the whole square into SFL. The starting current reduced by S times IFL, my dears, S time IFL. Okay, so it will be equal to X square into ISC divided by IFL into SFL. X times X square into square, X square into ISC divided by IFL the whole square into SFL. Bus. Okay, it is simple actually. There is a tapped voltage. That tapped voltage will be X times X will be less than 1. X time as that of the what applied voltage, definitely that will be the voltage. So that current will be no series, no, conductor will be in series, no. So that will be equal to what? That will be equal to X times the applied voltage divided by Z, X into V by Z. Okay, is there any doubt? Is there any doubt? Is there any doubt? Okay, this X is nothing but the tapped portion. Up to this we will have a current of ISC. So up to this there will be X times ISC. Okay, X time ISC. Okay, so this will be the what? Starting torque to the full load torque. X square into ISC divided by IFL the whole square into SFL. Okay, so these are the three types of starter. We just need three equation from this three starter. Not the working and all will be. No one will ask. No one will ask. Auto transformer starter means instead of transfer we just use an auto transformer. Slowly we increasing the supply. If what the motor picks up the normal speed, if you feel when we adjust the auto transformer to the rated voltage bus. That's all. So next we have to see the three important relation. Just you want to note this relation. T start by TFL in terms of first DOL. What was that? ISC divided by IFL into whole square into SFL. Okay, next T start by TFL in what? Star delta star, which is equal to what, my dears? In star delta 1 by 3 into ISC by IFL the whole square into SFL. And next T start by TFL in auto transformer starter. Auto transformer starter will be equal to X square into ISC divided by IFL into what? SFL. X square into ISC divided by IFL. This X will be less than 1. X will be less than 1. Okay, these three equations you just want to remember all the time, because this is directly asking you problems. In problem only it can be utilized. So you just want to know these three equations. Okay, you just have an idea of what is happening in the starter and you just thoroughly by heart this equation. But ISC is nothing but the starting current when DOL starter, there is no starter. That is the ISC. IFL is nothing but the rated full load current. The rated full load current. Without any starter, my dears. Without any starter, rated full load current. And changes will be happened in, suppose we are using star delta, change will be 1 by 3. Suppose you are using auto transformer, change will be X square bus. The remaining terms, no, this is nothing but without any starter, the relationship between starting torque and full load bars. If you cover this equation, it will give without a starter. If you cover X square, it will give without a starter. The factors are this is 1 by 3 for auto transformer, X square for auto transformer, and 1 by 3 for what? Star delta. You just need to remember this equation, 3 equation. Okay, that's all. Okay. I think I am making you very much confused, right? I am making you very much confused, my dears. Okay. So if you want to ask what is the ratio of, suppose in a question, if you ask question, suppose in a question you ask, what is the starting torque to, what is the ratio of starting torque to full load torque in DOL and star delta. Direct question may ask like this. Many times I have seen this question. Direct question. Simply you have to divide this. So T start by TFL for DOL, you know that is that. What is that? T start for TFL for DOL divided by T start by TFL for star delta bus. So it will be equal to what? ISC divided by IFL the whole square into SFL whole divided by 1/3 into ISC by IFL the whole square into SFL. These term all cancel. The result will be simply what, my dears? 3. So this is the answer. Like that questions you may expect. So that was the whole function of doing the whole derivation, and I think I confused you also. Okay, I tried to deliver what I exactly imagined. That is why you may feel slight confusion and all. But finally we came there, right? Finally we came there. So that is the equation. T start by TFL will be equal to for DOL and star delta. This is the question. Or in another question you may ask, what is the ratio of starting torque to full load torque in DOL and auto transformer starter? And what will be 1/x square? Next, then second question also given like DOL and auto transformer. Suppose it is in DOL and auto transformer. What will be the answer? We will do that also. Question will be from this. Question will be from that relationship. Okay. Next question you may expect like same. What is the starting torque? What is the ratio of? I will explain. I will write. What is the ratio of T start to TFL in DOL and auto transformer starter? What will be that? What is the ratio of T startup to TFL in DOL and auto transformer? What is that? Okay, we will write that also. T startup by TFL in DOL by T startup by TFL in auto transformer. So it will be equal to what? ISC divided by IFL the whole square into SFL whole divided by what, my dears? X square into ISC by IFL the whole square into SFL. The whole terms will cancel. The remaining will be simply 1/x square. Where x is nothing, the tapped portion. That you may directly given in the question. Did you get what I mean? Did you get what I meant? Okay, let's do a problem so that you can apply the things. Okay. Okay, write a question. A small three-phase induction motor. A small three-phase induction motor. A short circuit current equal to a short circuit current equal to 5 times of full load current of full load current. Then determine the starting current and starting torque. Starting current and starting torque. If resistance starter is used, if resistance starter, that is nothing but auto transformer starter, right? Okay, I won't write that because in question you may give like this. If resistance starter is used to reduce the supply voltage to reduce the supply voltage to 60% of the normal voltage. At the full load slip of 0.05. How can we find that? How can we find that? A small three-phase induction motor, a short circuit current equal to 5 times of the full load current. Then determine the starting current, okay, and starting torque. If resistance starter is used to reduce the supply voltage to 60% of the normal voltage at the full load slip of 0.05, and IFL is equal to, let be 5 ampere. You assume IFL is equal to 5 ampere. Okay. So what is the first question? Current, determine the starting current, right? Starting current will be equal to what? Starting current is given in the question itself, which is equal to 5 times the full load current, correct? 5 times the full load current, or 5 into 5 is equal to 25 ampere. Okay. Next you have to find starting torque, correct? Starting torque. Okay, starting torque. So we have the relation as starting torque by TFL, full load torque, will be equal to, what is that? ISC divided by IFL, correct? ISC divided by IFL, the whole square into SFL for normal DOL starter, right? For normal DOL starter. It is given in the hint, it is given as a hint that in the question, if resistance starter is used to reduce the supply voltage to 60% means, how can we take that, my dears? How can we take that? X is equal to what? 60%, or which will be equal to 60 by 100, or which will be equal to 3 by 5 is less than 1, right? Am I correct? It's less than 1 now. So now this is assumed that this is a auto transformer starter. So T start for TFL for auto transformer. For auto transformer starter will be equal to what? X square into ISC divided by IFL, the whole square into SFL. So it will be equal to what, my dears? X is nothing but 3 by 5 the whole square. So 3 by 5 the whole square into ISC is nothing but what? 5 times, correct? 5 times the full load current now. So IFL, 5 times IFL divided by IFL, the whole square, into SFL is nothing but 0.05. So it will be equal to 9 by 25 into 25, correct? IFL could cancel, 25 into 0.05. So 25 and 25 get it, 9 into 0.05 will be equal to 0.45. So this will be equal to T start by TFL, or T start will be equal to 0.45 TFL. This is the answer. This is the answer. This is the answer. Okay, did you get the idea? Did you get the idea, my dears? Okay, what is the time now? What is the time now? 5:53. Okay, 5:53. Okay, my dears, so let's see tomorrow with a new session. Okay, so bye for today and let's meet again. Bye.